All right. Well, thank you everyone for joining us, and welcome to another meeting of PhillyXP. When we were in person, we're based in the Philadelphia area, but for a while now we've been fully virtual, which is nice because we get to welcome people from all over and speakers from all over, which is great. Anthony's not here, is he? Anthony Harplumby to do his sponsorship.
I've not seen him. Nope.
Maru, I'm back. Shush, 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 you schmuck. Maru, I'm back. Shush, you schmuck. You look like a me.
All right. Anyway, so anyway, we have another meetup scheduled that we just posted out for next month. So please check that out. And we're very happy to welcome Dave Farley today to be our featured speaker. He's going to be reading from his new book and taking questions. He's a pioneer in the area of continuous delivery. He was a co-author of the book Continuous Delivery, and he has a wildly successful YouTube channel about software development that you should definitely check out. He also posted a link for a discount to his new training course, and we'll make sure that gets posted again in the chat towards the end of the meetup. So anyway, without further ado, do you want to get started, Dave?
Sure, and welcome everybody. Thanks for joining us. It's evening for me, so thanks for joining us this evening, or whatever time zone you're in. I'm going to be reading an excerpt. I'm going to be reading an excerpt from my new book, which is called Modern Software Engineering. The idea behind the book really was I've been working for a number of years, a lot of years. I'm old, and doing various different things. And during the early part of my career, I had sort of job titles like software engineer or junior software engineer or whatever it might be. And later on, I started working for companies that didn't really like the term engineering, and neither did I really, to be honest. And then I started doing some things that required some more focus and some more precision in the kinds of approaches that we were taking. And I started to think that there was something more to the idea of engineering, but maybe not in the way that most people think of it. And really that was the impetus, I suppose, for me to start writing this book. I think that there are some ideas. I think that there's a growing consensus about what really works in software development. And I think that we're getting some data that backs some of the assertions that I make in my book and in other places up and kind of reinforces some of those opinions. And I think that we're starting to see patterns where there are common practices that you can see in the organizations and teams that we all think of as being exemplary in our field. And I wanted to try and I wanted to attempt with this book to try and pull some of those ideas together. The other thing that I will say is that although I'm reasonably used to public speaking, I'm not used to reading my book out loud. I've not done this before, so I'm probably going to stumble a bit and all that sort of thing, but hopefully you'll just put up with it. I will read for a little while, half an hour or 40 minutes or so, and I'm going to start from the first chapter because I think that's a good lead in an introduction to what my book is about and some of the ideas. I hope it is. And then I will leave plenty of time for questions at that point. So I'm also going to, I tend to have a slightly more formal voice when I write than I do when I talk. So if it sounds a bit English and a bit pretty, that's because that's the way that I write. Sorry about that. So I'll start going, and I will read out kind of headings and subheadings and things just to position you in case you do read the book or you're interested in what it is that I mean to talk about. So starting on chapter 1 with the introduction, which is, and the next subheading is engineering, the practical application of science. So software development is a process of discovery and exploration. Therefore, to succeed at it, software engineers need to become experts at learning. Humanity's best approach to learning is science, so we need to adopt the techniques and strategies of science and apply them to our problems. This is often misunderstood to mean that we need to become physicists, measuring things to unreasonable, at least in the context of software, levels of precision. Engineering is much more pragmatic than that. What I mean when I say that we should apply the techniques and strategies of science is that we should apply some pretty basic, but nevertheless extremely important ideas. The scientific method that most of us learned about in school is described by Wikipedia as characterize, make an observation of the current state, hypothesize, create a description, a theory that may explain your observation, predict, make a prediction based on your hypothesis, and experiment, test your prediction. When we organize our thinking this way and start to make progress on the basis of many small informal experiments, we begin to limit our risk of jumping to inappropriate conclusions and end up doing a better job as a result. If we start to think in terms of controlling the variables in our experiments so that we can achieve more consistency and reliability in our results, this leads us in the direction of a more deterministic systems and code. If we start to think in terms of being skeptical about our ideas and explore how we could falsify them, we can identify and then eliminate bad ideas more quickly and make progress much faster. This book is deeply grounded in a practical, pragmatic approach to solving problems in software, based on an informal adoption of basic scientific principles. In other words, engineering. What is software engineering? My working definition of software engineering that underpins the ideas in this book is this. Software engineering is the application of an empirical, scientific approach to finding efficient economic solutions to practical problems in software. The adoption of an engineering approach to software development is important for two main reasons. First, software development is always an exercise in discovery and learning. And second, if our aim is to be efficient and economic, then our ability to learn must be sustainable. This means that we must manage the complexity of the systems that we create in ways that maintain our ability to learn new things and adapt to them. So we must become experts at learning and experts at managing complexity. There are 5 techniques that form the roots of this focus on learning. Specifically, to become experts at learning, we need the following: iteration, feedback, incrementalism, experimentation, and empiricism. This is an evolutionary approach to the creation of complex systems. Complex systems don't spring fully formed from our imaginations. They're the product of many small steps where we try our ideas and react to success and failure along the way. These are the tools that allow us to accomplish that exploration and discovery. Working this way imposes constraints on how we can safely proceed. We need to be able to work in ways that facilitate the journey of exploration that is at the heart of every software project. So, as well as having a laser focus on learning, we need to work in ways that allow us to make progress when the answers and sometimes even the direction is uncertain. For that, we need to become experts at managing complexity. Whatever the nature of the problem that we solve or the technologies that we use to solve them, addressing the complexity of the problems that face us and the solutions that we apply to them is a central differentiator between bad systems and good. To become experts at managing complexity, we need the following: modularity, cohesion, separation of concerns, abstraction, and loose coupling. It's easy to look at these ideas and dismiss them as being familiar. Yes, you're almost certainly familiar with all of them. The aim of this book is to organize them and place them into a coherent approach to developing software systems that helps you to take best advantage of their potential. This book describes how to use these 10 ideas as tools to steer software development. It then goes on to describe a series of ideas that act as practical tools to drive an effective strategy for any software development. These ideas include the following: testability, deployability, speed, controlling the variables, and continuous delivery. When we apply this thinking, the results are profound. We create software with higher quality. We produce work more quickly. And the people working on the teams that adopt these principles report that they enjoy their work more, feel less stressed, and have a better work-life balance. These are extravagant claims, but again, they're backed by the data. Reclaiming software engineering. I struggled over the title of this book, not because I didn't know what I wanted to call it, because our industry has so redefined what engineering means in the context of software that the term has become devalued. In software, it's often seen as either a synonym for only code or something that puts people off as being overly bureaucratic and procedural. For true engineering, nothing really could be further from the truth. In other disciplines, engineering simply means the stuff that works. It is the process and practice that you apply to increase your chances of doing a good job. If our software engineering practices don't allow us to build better software faster, then they aren't really engineering, and we should change them. That's the fundamental idea at the heart of this book, and its aim is to describe an intellectually consistent model that pulls together some foundational principles that sit at the roots of all great software development. There's never any guarantee of success, but adopting these mental tools and organizing principles and applying them to your work will certainly increase your chances of success. How to make progress. Software development is a complex, sophisticated activity. It is in some ways one of the more complex activities that we as a species undertake. It is ridiculous to assume that every individual or even every team can and should invent how to approach it from scratch every time we begin a new piece of work. We've learned and continue to learn things that work and things that don't. So how can we as an industry and as teams make progress and build on the shoulders of giants, as Isaac Newton once said, if everyone has a veto on everything? We need some agreed principles and some discipline that guide our activities. The danger in this line of thinking is that if misapplied, it can lead to draconian, overly directive decision from authority style thinking. We will fall back on previous bad ideas where the job of managers and leaders is assumed to be to tell everybody else what to do and how to do it. The big problem with being prescriptive or overly directive is, what do we do if some of our ideas are wrong or incomplete? In fact, they inevitably will be. So how can we challenge and refute old but well-established bad ideas and evaluate novel, potentially great, untried ideas? We have a very strong example of how to solve these problems. It's an approach that allows us the intellectual freedom to challenge and refute dogma and to differentiate between fashion, plain old bad ideas, and great ones, whatever their source. It allows us to replace the bad ideas with better ideas and to improve on the good ideas. Fundamentally, we need some structure that allows us to grow and evolve improved approaches, strategies, processes, technologies, and solutions. We call this good example science. When we apply this kind of thinking to solving practical problems, we call it engineering. This book is about what it means to apply scientific style reasoning to our discipline and so achieve something that we can genuinely and accurately refer to as software engineering. The birth of software engineering. Software engineering as a concept was created at the end of the 1960s. The term was first used by Margaret Hamilton, who later became the director of the software engineering division of the MIT Instrumentation Lab. Margaret was leading the effort to develop the flight control software for the Apollo space programming. During the same period, the North Atlantic Treaty Organization, NATO, convened a conference in Garmisch-Partenkirchen, Germany, to try and define the term. This was the first ever software engineering conference. The earliest computers had been programmed by flipping switches or even hard-coded as part of their design. It quickly became clear to the pioneers that this was slow and inflexible, and the idea of the stored program was born. This was the idea that for the first time made a clear distinction between software and hardware. By the late 1960s, computer programs had become complex enough to make them difficult to create and maintain in their own right. They were involved in solving more complex problems and were rapidly becoming the enabling step that allowed certain classes of problems to be solved at all. There was perceived to be a significant gap between the rate at which progress was being made in hardware compared to the rate at which it was being made in software. This was referred to at the time as the software crisis. The NATO conference was convened in part in response to this crisis. Reading the notes of the conference today, there are many ideas that are clearly durable. They've stood the test of time and are as true today as they were in 1968. That should be interesting to us. If we aspire to identify some fundamental characteristics that define our discipline. A few years later, looking back, Turing Award winner Fred Brooks compared the progress in software to that in hardware. He said, "There's no single development in either technology or management technique which by itself promises even one order of magnitude improvement within a decade in productivity, reliability, or simplicity." Brooks was saying this in comparison to the famous Moore's law, which hardware development had been tracking for many years. This is an interesting observation and one that I think would surprise many people, but in essence has always been true. Brooks goes on to state that this is not so much a problem of software development, it's much more an observation on the unique, staggering improvement in hardware performance. Quoting Brooks again, "We must observe that the anomaly is not that software progress is so slow, but that computer hardware progress is so fast. No other technology since civilization began has seen 6 orders of magnitude price performance gain in 30 years. He wrote this in 1986. What we would think of today as the dawn of the computer age. Progress in hardware since then has continued at the pace that he was describing. And the computers that seemed so powerful to Brooks look like toys compared to the capacity and performance of modern systems. And yet, his observation on the rate of improvement in software development remains true. Shifting the paradigm. The idea of a paradigm shift was created by physicist Thomas Kuhn. Most learning is a kind of accretion. We build up layers of understanding, with each layer foundationally underpinned by the previous one. However, not all learning is like that. Sometimes we fundamentally change our perspective on something, and that allows us to learn new things, but it also means that we must discard what went before. In the 18th century, reputable biologists, they weren't called that then, believed that some animals spontaneously generated themselves. Darwin came along in the middle of the 19th century and described the process of natural selection, and this overturned the idea of spontaneous generation completely. This change in thinking ultimately led to our modern understanding of genetics, our ability to understand life at a more fundamental level, create technologies that allow us to manipulate these genes and create COVID-19 vaccines and genetic therapies. Similarly, Kepler, Copernicus, and Galileo challenged the then conventional wisdom that Earth was at the center of the universe. They instead proposed a heliocentric model for the solar system. This ultimately led to Newton creating the laws of gravitation and Einstein creating general relativity, and it allowed us to travel in space and create technologies like GPS. The idea of paradigm shift implicitly includes the idea that when we make such a shift, we will, as a part of that process, discard some other ideas that we now know are no longer correct. The implications of treating software development as a genuine engineering discipline rooted in the philosophy of the scientific method and the scientific rationalism are profound. It's profoundly not only, it's profound not only in its impact and effectiveness, described so eloquently in the Accelerate book, that's by Nicole Fosgren, Gene Kim and Jess Humble, but also in the essential need to discard the ideas that this approach supersedes. This gives us an approach to learning more effectively and discarding bad ideas more efficiently. I believe that the approach to software development that I describe in this book represents such a paradigm shift. It provides us with a new perspective on what it is that we do and how we do it. Summary of the first chapter. Applying this kind of engineering thinking to software does not need to be heavyweight or overly complex. The paradigm shift in thinking differently about what it is that we do and how we do it when we create software should help us to see the wood for the trees and make this simpler, more reliable and more efficient. This is not about more bureaucracy. It's about enhancing our ability to create high quality software more sustainably and more reliably. Chapter 2, what is engineering? I've been talking to people about software engineering for some years now. As a result, I regularly get involved in a surprising number of conversations about bridge building. They usually start with the phrase, yes, but software isn't bridge building, as though this was some kind of revelation. Of course, software engineering is not the same as bridge building. But what most software developers think of as bridge building isn't like real bridge building either. The conversation is really a form of confusion between production engineering and design engineering. Production engineering is a complex problem when the discipline involved is dealing with physical things. You need to get those physical things created to certain levels of precision and quality. You need your widgets delivered to some specific location in space at a particular time, to a defined budget, and so on. You need to adapt theoretical ideas to practical reality as your models and designs are found to be lacking. Digital assets are completely different. Although there are some analogues to these problems for digital artifacts, these problems either don't really exist or can be made trivially simple. The cost of production of digital assets of any kind is essentially free, or at least should be. Production is not our problem. For most human endeavour, the production of things is the hard part. It may take effort and ingenuity to design a car, an airline, or a mobile phone, but taking the initial prototype design and idea into mass production is immensely more expensive and complicated. That is particularly true if we aim to do it with any kind of efficiency. As a result of these difficulties, we, products of the industrial age and industrial age thinking, automatically, almost unthinkingly, worry about this aspect, the production of any significant task. The result of this in software has been that we've fairly consistently tried to apply production style thinking to our industry. Waterfall processes are production lines for software. They are the tools of mass production. They're not the tools of discovery, learning, and experimentation that are, or at least should be, at the heart of our profession. Unless we're foolish in our software development choices, for us, production consists of triggering the build. It's automatic, push button, immensely scalable, and so cheap that it's best considered to be free. We can still make mistakes and get it wrong, but these are problems that are well understood and well addressed by tools and technology. Production is not our problem. This makes our discipline unusual. It also makes it subject to easy misunderstanding and misapplied thinking and practices because this ease of production is so unusual. Design engineering, not production engineering. Even in the real world, what most people think of as bridge building is different if the bridge builders are building the first of a new kind of bridge. In this circumstance, you have two problems, really. One that is relevant to software development and one that is not. First, the one that's not. When building even the first of a new kind of bridge, because it is physical, you have all of the production problems and many more that I mentioned. From a software perspective, these can be ignored. Second, in the case of bridge building, is that in addition to those production problems, if you are building the first of a new kind of bridge, the second really difficult part is the design of your new bridge. This is difficult because you can't iterate quickly when your product is something physical. When building physical things, they're difficult to change. As a result, engineers in other disciplines adopt modeling techniques. They may choose to build small physical models, and these days probably computer simulations of their design or mathematical models of various kinds. In this respect, we software developers have an enormous advantage. A bridge builder may create a computer simulation of their proposed design, but this will only be an approximation of the real thing. Their simulation, their model, will be inaccurate. The models that we create as software, our computer simulations of the problem, are our product. We don't need to worry if our models match reality. Our models are the reality of our system, so we can verify them. We don't need to worry about the cost of changing them. They're software, thus they're dramatically easier to change, at least when compared to a bridge. Ours is a technical discipline. We like to think of ourselves in this context, and my guess is that the majority of people who think of themselves as professional software developers probably have had some form of science in their education or past. Despite this, little software development is practiced with scientific rationalism in mind. In part, this is because we took some missteps in our history. In part, it's because we assume that science is hard, expensive, and impossible to achieve within the scope of normal software development schedules. Part of the mistake here is to assume some level of idealistic precision that is impossible in any field, let alone the field of software development. We've made the mistake of seeking mathematical precision, which is not the same thing as engineering. I'm going to skip over a sidebar and continue with the main thrust of the chapter. The sidebar, just for interest, is called Engineering as Maths. As I write this book, SpaceX is busy blowing up rockets while it works to perfect Starship. It has certainly built mathematical models of nearly every aspect of the design of its rockets, its engines, the fuel delivery systems, launch infrastructure, and everything else. But then it tests them. Even something seemingly simple, like switching from 4mm stainless steel to 3mm stainless steel, may sound like a pretty controlled change. SpaceX has access to detailed data on the tensile strength of the metal, its experience and data collected from tests that show exactly how strong pressure vessels constructed from the 4mm steel are. Yet still, after SpaceX crunched the numbers, it built experimental prototypes to evaluate the difference. It pressurized these test pieces to destruction to see if their calculations were accurate and gain deeper insight. SpaceX collected data and validated its models because these models will certainly be wrong in some esoteric, difficult to predict way. The remarkable advantage that we have over all other engineering disciplines means that the models that we create in software are the executable result of our work, so that when we test them, we are testing our products, not our best guess of the reality of our products. If we work carefully to isolate the part of the system that we're interested in, we can evaluate it in exactly the same environment that it will be exposed to in production. So our experimental simulation can much more precisely and much more accurately represent the real world of our systems than in any other discipline. In his excellent talk called Real Software Engineering, Glenn Vanderberg says that in other disciplines, engineering means the stuff that works. And that almost the opposite has become true for software. Vanderberg goes on to explore why this is the case. He describes an academic approach to software engineering that was so onerous that almost no one who practiced it would recommend it for future projects. It was heavyweight and added no significant value to the process of software development at all. In the telling phrase, Vanderberg says, this academic software engineering process only worked because sharp people who cared were willing to circumvent the process. That's not engineering by any sensible definition. Vandenberg's description of engineering as the stuff that works is important, though. If the practices that we choose to identify as engineering don't allow us to make better software faster, then they don't qualify as engineering. Software development, unlike all physical production processes, is wholly an exercise in discovery, learning, and design. Our problem is one of exploration, and so we, even more than the spaceship designers, should be applying the techniques of exploration rather than the techniques of production engineering. Ours is solely a discipline of design engineering. So if understanding of engineering is often confused, what is engineering really about? I'm going to skip another sidebar in the book, which describes Margaret Hamilton's work on the Apollo program as the first software engineer. Moving on, a working definition of engineering. Most dictionary definitions of the word engineering include the common words and phrases, like the application of maths, empirical evidence, scientific reasoning within economic constraints. And I propose the following definition, which I'm repeating, I guess. Engineering is the application of an empirical scientific approach to finding efficient economic solutions to practical problems. All of the words here matter. Engineering is applied science. It's practical, using empirical means to learn and advance understanding and solutions toward the resolution of a problem. The solutions that engineering creates are not abstract ivory tower things. They're practical and applicable to the problem and the context. They're efficient and they're created with an understanding of and constrained by the economics of the situation. Engineering is not equal to code. Another common misperception of what engineering means when it comes to software development is that engineering is only the output, the code, or perhaps its design. This is too narrow an interpretation. What does engineering mean to SpaceX? It's not the rockets. They are the products of engineering. Engineering is the process of creating them. There is certainly engineering in the rockets, and they are certainly engineered structures, but we don't see only the act of welding the metal as engineering unless we have a weirdly narrow view of the topic. If my definition works, then engineering is about applying scientific rationalism to solving problems. It is the solving of the problems where the engineering really comes to play, not just the solutions themselves. It's the process, tools, and techniques. It's the ideas, philosophy, and approach that together make up an engineering discipline. I had an unusual experience while writing this book. I published a video about the failure of a game on my YouTube channel, which was dramatically more popular than most of my videos. The most common negative feedback I got in saying that this was a failure of software engineering was that I was blaming programmers and not their managers. I meant that it was a failure in the whole approach of producing software. The planning was bad, the culture was bad, the code was bad. There were lots of bugs, apparently. So for this book, when I talk about engineering, unless I qualify it specifically, I mean everything that it takes to make software. Process, tools, culture are all part of the whole. Skipping over another sidebar, which is called the evolution of programming languages. Why does engineering matter? Another way to think of this is to consider how we go about the production of things that help us. For the vast majority of human history, everything that we created was the product of craft. Craft is an effective approach to creating things, but it has its limits. Craft is very good at creating one-off items. In a craft-based production system, each item will inevitably be unique. In its purest sense, this is true of any production system, but in a craft-based approach, it's more true because the precision and so the repeatability of the production process is generally low. This means that the amount of variance between individually crafted artifacts is higher. Even the most masterful of craftspeople will create items with only human level of precision. This seriously impacts the ability of craft-based systems to reproduce things reliably. Grace Hopper said, "To me, programming is more than an important practical art. It's also a gigantic undertaking in the foundations of knowledge. The limits of craft. We often have an emotional reaction to craft-based production. As human beings, we like the variance. We like the feeling that our treasured, handcrafted thing embodies the skill, love, and care of the craftsperson that created it. However, at the root, craft-based production is fundamentally low quality. A human being, however talented, is not as accurate as a machine. We can build machines that can manipulate individual atoms, even subatomic particles, but a human being is extraordinarily talented if they can produce something manually with the accuracy of 1/10 of a millimeter. How does this precision matter in software? Let's think about what happens when our programs are executed. A human being can perceive change, any change, at the limit of approximately 13 milliseconds. To process an image or to react to something takes hundreds of milliseconds. At the time of writing, the most modern consumer-level computers operate on a clock cycle of around about 3 gigahertz. That is 3 billion cycles per second. Modern computers are multi-core and operate on instructions in parallel, so often they process more than one instruction per cycle. But let's ignore that and imagine, for simplicity, that each machine instruction that moves values between registers, adds them, or references some in-cache piece of memory takes a single clock cycle. That is 3 billion operations per second. If we do the math and calculate how many instructions a modern computer can crunch through in the absolute minimum time that a human being could perceive any external event, that number is 39 million instructions. If we limit the quality of our work to human scale perception and accuracy, we are at the very best sampling what's going on at a rate of 1 in 39 million. So what are our chances of missing something? Precision and scalability. The difference between craft and engineering highlights two aspects of engineering that are important in the context of software precision and scalability. Precision is obvious. We can manipulate things at much higher resolution of detail through the application of engineering techniques than by hand. Scalability is perhaps less immediately obvious, but is even more important. An engineering approach is not limited in the same way that craft-based approach is. The limits of any approach that relies on human capability is ultimately limited by the human capability. If I dedicate myself to achieving something extraordinary, I may learn to paint a line, file a piece of metal, or stitch leather car seats to within tiny fractions of a millimeter. But however hard I try, however gifted I may be, there are hard limits to how accurate human muscles and senses can be. An engineer, though, can create a machine to make something smaller and more precise. We can build machines, tools, to make smaller machines. This technique is scalable all the way down to the limits of quantum physics and all the way up to the limits of cosmology. There's nothing, at least in theory, to prevent us via the application of engineering to manipulate atoms and electrons, as we already do, or stars and black holes, as one day we may. To put this more clearly into the context of software, if we are very skilled and train very hard, we could perhaps enter text or click buttons quickly enough to test our software at a rate where we could imagine being able to carry out a test of our software in a few minutes. Let's imagine, for the sake of comparison, that we can carry out one test of our software every minute, not a pace that I could imagine myself being able to sustain for very long. If we could run a test per minute, we are under testing compared to a computer by hundreds of thousands, probably millions of times. I've built systems that ran around 30,000 test cases in 2 minutes. We could have scaled that considerably further, but had no reason to do so. Google claims to run 150 million text executions per day. That works out at 104,166 tests per minute. Not only can we use our computers to test hundreds of thousands of times more quickly than a human being, we can sustain that pace for as long as we have electricity for our computers. That is scalable. managing complexity. There's another way in which engineering scales, where craft does not. Engineering thinking tends to lead us to compartmentalize problems. Before the American Civil War in 1860, if you wanted a gun, you went to a gunsmith. The gunsmith was a craftsman, and he was usually a man. The gunsmith would create a whole gun for you. He would understand every aspect of that gun, and it would be unique to you. He would probably give you a mold for your bullets, because your bullets would be different to everybody else's and specific to your gun. If your gun had screws, each one was almost certainly different from all of the others because it would have been handmade. The American Civil War was unique in its day. It was the first war where arms were mass produced. There is a story of the man who wanted to sell rifles to the northern states. He was an innovator, and it seems a bit of a showman. He went to Congress to make his case to get the contract to make the rifles for the armies of the northern states. He took with him a sack of rifle components. As part of his presentation to the congressman, he emptied the bag of components onto the floor of Congress and asked the congressman to select components from the pile. From these components, he assembled a rifle, won the contract, and invented mass production. This was the first time that this kind of standardization was possible. A lot of things had to happen to make it possible. Machines, tools had to be engineered to make components that were repeatably identical to one another within some defined tolerance. The design had to be modular so that the components could be assembled, and so on. The result was devastating. The American Civil War was, in essence, the first modern war. Hundreds of thousands of people were killed because of the mass production of armaments. These arms were cheaper, easier to maintain and repair, and more accurate than those that had gone before. All this was because they were engineered with more precision, but also because there were lots more of them. The process of production could be de-skilled and scaled up. Instead of needing an expert master craftsperson for every weapon, the machinery in the factory could allow less skilled people to create rifles of comparable precision to a master. Later, as tooling, production techniques, and engineering understanding and discipline increased, these mass-produced weapons exceeded the quality as well as the productivity of even the greatest master craftsmen, and at a price that anyone could afford. A simplistic view may interpret this as a need to standardize or a need to adopt mass production for software, but this is once again confusing the fundamental nature of our problem. This is not about production, it's about design. If we design a gun that's modular and componentized in a way that the arms manufacturers of the American Civil War did, then we can design parts of that gun more independently. Viewing this from a design perspective rather than from a production or engineering or manufacturing perspective, we've improved our management of the complexity of building guns. Before this step, the gunsmith, master craftsman, would need to think of the whole gun if they wanted to change some aspect of its design. By componentizing the design, the Civil War manufacturers could explore changes incrementally to allow them to improve the quality of their products step by step. Edgar Dijkstra said, "The art of programming is the art of organizing complexity." I think I've probably read enough. I'm going to skip forward to the summary for this chapter. There's a few more bits, but I'm going to jump over those and just read the summary for the chapter to kind of round off this part of tonight's thing. Summary. In software, we've somewhat redefined what engineering means. Certainly in some circles, we've come to see engineering as an unnecessary, onerous, burdensome thing that gets in the way of real software development. Real engineering in other disciplines is none of these things. Engineers in other disciplines make progress more quickly, not less. They create work of higher quality, not lower. When we begin to adopt a practical, rational, lightweight, scientific approach to software development, we see similar benefits. Software engineering will be specific to software, but it will also help us to build better software faster, not get in the way of us doing that. Thank you. That's the end of my reading for tonight. So I'm very happy to take any questions that anybody has.
Anyone want to get started?
How do you see the work for the book Accelerate and the former Dora surveys factoring into your view of using science in software engineering?
I think that they're an important step. I think that they did something. I refer to those in the next chapter of the book from where we finished reading. But I think that I think that they've done something important and answered a question that had been on people's minds for a very long time. So people worried for a long time about how do you compare, software development in different teams, and we tried all sorts of things. And again, we fell into the trap of thinking in production terms. So we tried really hard to measure productivity. And as we've just discussed, that's not really our problem. So what the Dora metrics did, that I think was interesting, was take a very different take on this. The Dora metrics are based around two ideas, stability and throughput. Stability is a measure of the quality of the work that we produce. Primarily, stability is measured from the rate at which we introduce mistakes into our code and the time it takes us to recover from mistakes when we find them. And those are good measures, good proxies for measuring the quality of our systems. And then throughput is about the efficiency with which we're able to produce work of that quality. And that's measured again by two different measures usually. So how long it takes you to go from idea to something useful, and how frequently you can kind of release a change into production. And so we've got these two measures that evaluate the quality of our work and the rate at which we can produce work of that quality. Combined, those give us a predictive tool that can say, if you get high scores in stability and throughput, we can make predictions. We can make predictions of what it is that you're doing to achieve those scores, and we can make predictions of what kinds of outcomes you will get. You will get higher job satisfaction in the people that work on those things. You'll get the companies that employ us with teams with high scores in those things will make more money than other teams. This is all really good stuff, and it gives us a kind of measuring stick that we can use to measure ideas. So we could do things like, we could measure almost anything. Let's imagine that we decided that we wanted to change the framework that we're using for developing our UI code. So we could try an experiment. We could, if we've got a baseline measures of our stability and throughput, we could try adopting the new technology for a while and see whether it moved the dial on our measures of stability and throughput. Does it improve the quality of the work that we produce? Does it improve the efficiency with which we produce work? If it doesn't change either of those things, or it makes either of those things worse, it's not a good change. So I think that's quite a good measuring stick. There are some limits to how far you can go to trust the measures. It's after all, ultimately, it's sociology, and sociology isn't quantum physics. It's not as accurate. It's a bit more vague, a bit more statistical. But the Dora metrics are the most defensible statistical analysis of software development that we have so far. So I think they're a fantastic tool, and I think that we should use them to guide us, to steer us in the direction of doing better. I think that they make a good counterpoint, I suppose, or supporting role to the other ideas that I'm talking about in the book. The book goes on to, it's structured around the ideas that I introduced in the first chapter, which are the ideas for managing, for optimizing for learning, the ideas for managing complexity. And then it's kind of wrapped up with practices that amplify our ability to achieve those. And I listed all of those during the reading. So the reason that I think that those ideas are important is because I think that we can use those as a different kind of qualitative measuring stick. So if you've got a choice in design, technology, team organization, whatever else, and you want to know whether it's a good choice or a bad choice, you could look at the Dora metrics. That's one really useful way of looking at them. And you could look at, does this choice improve the modularity of my design? Does it improve the cohesion in my code base? Does it improve the separation of concerns in my design, or reduce the coupling, or provide better lines of abstraction? Does it allow me to work more incrementally and make progress in small steps? Does it allow me to work more iteratively and gather feedback and learn from that feedback and steer my work and my designs and my products in small steps? All of these things are tools that allow us to make a judgment. If these days I've become so infected by these ideas, these days almost any choice that I make about in software is colored by this sort of thinking. So if I'm looking at whether to adopt a new technology into my business, I'm thinking about those things. Do they allow me to, does it allow me to iterate faster? You know, can I do simple things like version control it, so I can make change in small steps safely and so on? Does it allow me to modularize my system better and compartmentalize it more effectively? And all of these things, these are the tools that help steer me in the direction of doing at least a better job than I could do without them. So I think that the Dora metrics are supporting to these things. In the context of the Accelerate book, Accelerate was really written to, you know, to try and collect evidence to see what worked. And what it found was that continuous delivery as an approach works better than anything else that we've measured so far. And that's where, you know, on these measures, and, you know, that idea is reinforced. So the ideas that I'm talking about in my book are deeply continuous delivery ideas and deeply in line with the Dora metrics and that line of thinking. So I think they're extremely valuable. And I think that they're one of the more important things that has happened over the last few years. It's one of the more important books that's been released in the last 10 years, in my opinion, at least. Somebody's got, Joey's you've got your hand up.
Yeah. How you doing, Dave?
I'm good,
can you hear me?
Yes, I can.
All right, perfect. I just wanted to, it's not really a question or anything. It's more just like a huge thank you for so I'm very new in my software engineering journey. Started about, I'm doing a software engineering bootcamp right now. There's actually a couple co-eds in this with me, so that's pretty cool. And the way you approach software engineering with a scientific method, that just kind of like painted a very clear picture as to why I'm enjoying this journey so much. So thank you for that. I really appreciate that. I was very bad at school, so the only thing that I really did enjoy doing was like science projects and learning the scientific method and stuff like that. So huge thank you for kind of just painting that picture for me so I can better understand why I'm enjoying it so much, and also so that I can finally start applying that in a more disciplined way, approaching these problems that I'm going to be solving in the future. So yeah, thank you, man. Really appreciate it.
Well, it's a pleasure. Thank you for the thanks. You saying about, you know, enjoying science as, you know, at school and so on. I think kids are natural scientists. I have two very young granddaughters, and just watching them learn and, you know, discover new things and try stuff out is a joy to watch. But I think that's it's both kind of natural to us and kind of unnatural to us. The trouble is to do science is kind of fascinating and enjoyable and fun, but also it takes a little bit of discipline in organizing our thoughts, because there's a beautiful quote from my favorite and most people's favorite physicist. If any of you have a favorite physicist, it's likely to be the same as mine, Richard Feynman. Richard Feynman was a philosopher on science, and one of the things that Feynman said was that science is there to avoid us fooling ourselves, and we are the easiest people to fool. And I quite like that. It's it's very easy for us to misunderstand things, and the way in which we really get to learn, that we really get to understand whether something's a good idea or a bad idea, is just following this little line of science, the scientific method that just allows us a little bit more discipline in the way that we just evaluate ideas. And when we do that across the board in human experience, we solve problems better that way.
Absolutely. If
Garrett,
there was
you have your hand up.
Oh, Garrett has his hand. I'm sorry.
We want to go to Dimitro. I think Dimitro dropped a message in the chat.
Oh, I'm sorry.
First. Yeah, no worries.
Go ahead, Dimitro. I'm just reading the message. I'll read it out in case you haven't seen it. In your book, do you look at how to preserve the learning and discovery gained during the build phase of systems so that it remains available for access during the system's overall lifespan? Largely, the approach. I am somewhat well known in software circles for another book, which is called Continuous Delivery, which was quite successful as software development books go. Continuous delivery is about automating the production process. And one of the side effects of continuous delivery is that basically you get to tell the whole story about what happened in building and testing and releasing software. So you collect all of that data. For some kinds of software, that's really important. I spent the last 20 years mostly working in regulated environments in one form or another. I make a living these days as an independent software consultant, and I advise companies on software engineering. But mostly I work at the slightly more complex end, I suppose. So companies building scientific instruments or cars or medical devices, those kinds of things. And in those kinds of industries, then they're regulated. And so you have to be able to tell that story. And continuous delivery in this engineering discipline is one of the things that allows you to do that. But I don't want to paint the picture of what I'm talking about when I'm talking about engineering being bureaucratic. You don't need to write anything. All you need to write is tests and code. So that's documentation enough, if you do it well. There's nothing, you don't need any more than that. So I'm not talking about anything bureaucratic or complex here to do engineering. All I'm saying is that we organize our work to optimize for modularity, cohesion, separation of concerns, abstraction, and reduce coupling. We organize our processes to be iterative, feedback-driven, incremental, experimental, and empirical. And when we do those things, and apply other things like the skeptical mind, controlling variables, those kinds of science ideas. It's not about writing down lots and lots of screeds of documentation to support this. It's something else. Garrett, I think it's your turn now.
Thank you. So it's kind of curious. I've actually only recently picked up your book, which is kind of why I was interested to hear you speak. And I was going through and looking in it looks like there's large sections that you talk about test-driven development. Since this is an XP group, I was curious as to your perspective in terms of sometimes popular in terms of XP teams, sometimes hotly debated in the software engineering world at large of either pair or ensemble/mob programming, as it's called sometimes, and what's your opinion and perspective of those practices in your view of modern software engineering?
Firstly, let me put my cards clearly on the table. I'm an old school extreme programmer. I'm a full on XP guy. That's my background. I think continuous delivery became successful enough to become a kind of a agile methodology in its own right. People talk about being a continuous delivery team or something. I think continuous delivery is extreme programming, is second generation extreme programming. It's the same thing. I see no distinction. We slightly extended the range. Kent Beck said some nice things about continuous delivery as a book and as an idea. It's absolutely an 100% extreme programming to my mind. So you know, I think the extreme programming book was the most important book that's happened in my career, probably. So you asked about ensemble programming and so on. I think from an engineering perspective, there are two routes to proving that pairing or some form of ensemble programming is the best answer. And then there's some kind of pragmatic reasons that are helpful. So let me just talk a little bit about those. The data from the DORA reports say that continuous integration matters. It matters profoundly. One of the biggest predictors of success for a software development team is its ability to integrate all of the team's efforts at least once per day. That's the definition of continuous integration. So if continuous integration matters, then anything, and it predicts significant higher scores on stability and throughput if you do that. So if you're doing feature branching and running your tests, even if you are using Jenkins or Circle CI on your feature branches, it ain't continuous integration. So if it's continuous integration and you've got to evaluate your changes alongside everybody else's at least once per day, then anything that gets in the way of that is a problem. It means you're going to be doing a worse job. You're going to be writing worse software slower. That's what the data says. So if that's the case, we've got to do everything that we can to eliminate that. One of the problems, particularly if you're in a regulated environment, but even if you're not, you probably want a code review. It's good to have people look at your code. It's good to have people sanity check that you're not doing something crazy. So, you know, how do you organize those code reviews? That's the simplistic, naive, overly simplistic view of pairing, in my opinion. But still, let's take it. If you're looking at it from that perspective, then organizing code reviews cause a gate, and now you're in a difficult situation. Now you've got a complex process. In continuous delivery, we talk about working so our software is always in a releasable state. So continuous delivery slightly ups the ante on continuous integration. So not only does our code have to compile and work together, it also has to be releasable, which means we're going to automate everything else about the releasability of the system. If we want to get to that position, we want our deployment pipelines, the mechanism that we use to facilitate all of this, to be definitive. How do we do that where we've got code reviews? We could code review beforehand, which is pair programming, or we could put the code review as sort of a gating process afterwards. But now we've just that single step has massively complicated the problem, because now instead of having a binary situation, the software is releasable or it's not, the tests pass or they didn't, we've got a trinary situation that it's releasable or it's not yet evaluated or it's not releasable. And that's much more complicated to deal with. So pair programming allows us to get to up the feedback rate. It allows us to get the feedback into the development process. It brings it front and center into the development process. If that's all there was to it, I think that's a reasonable argument, but it's not, because pair programming also amplifies the human scale. One of the things that I am known for, I led a team that built one of the world's highest performance financial exchanges. We did some incredibly cool stuff. That was a full-on continuous delivery, extreme programming generation 2 team from the outset. We did some very cool things when we were building the teams, when we were building the exchange. And I think that one of the most important facets of that team was that we did full-on pair programming all of the time. And that was the tool that allowed us to grow as a team, to learn from one another in deep, important ways, and develop a genuinely, I'm being big-headed, but also accurate, a genuinely world-class development culture in that team. We did some genuinely world-class work in that team, and that was a result, I think, of pair programming. So I think it's important. I've tried mob programming, ensemble programming once for a day, so I can't talk it as from personal experience. I was a grumpy old man, and I used to say, yeah, why would you want to do that with all of those people? And then I realized I was playing all of the excuses that people make to me about pair programming back to the mob programmers, and I realized that I was being an old duffer and that I should try it. And I got invited to try it with a team, and I was blown away actually in that team by how well it worked. So I have an open mind about mobbing. Looks great to me, but I think I think pair programming is the liberating force that allows teams to learn. And if you don't do that, I don't think you can learn quite as well, if I'm honest, being hardline, having had half a glass of wine. I've been a bit over the top, but I think that's my stance. And I do. So one of the things that I should say to you is that my new book, the Modern Software Engineering book, is kind of, it's taken to try and give a rational description, a rational backing for test-driven development and continuous integration.
Got it.
Partly because I think that they are more profoundly true and valuable than people give them credit for. And I was trying to make that case and explain the reasons why I believe that to be true.
Thank you.
Pleasure.
Okay, I think I see just two more in the chat, a couple more in the chat.
Yeah. So based on your experience, how would you bring the practices and ideas described in the book to a dysfunctional team? That's a tough question. So first I try and make the team functional. And part of that is to use, probably to try and apply some pair programming. It's difficult. It's a difficult situation, and there can be problems. But software is, I'm going to say something that's maybe not horribly popular and may make you dislike me more than you do already if you do. But I think there's a degree to which you have to be fairly hardline. It depends what you're doing. So are we doing this for fun, or are we doing this for profit, or are we trying, are we having ambitions to do something fantastic? I did some work recently with organizations that were building medical devices that save people's lives. I want those things to work. I want I want the software for those things to have been built with care and attention and expertise and cleverness and done well. I think that stuff matters. And so if that's the case, then it's not for everybody it's not a matter of everybody being good enough to do that sometimes. So if you're trying to do something world-class, like this team was trying to do, then if you're operating at that sort of level, not everybody can play at that level. Before we started, I was talking with the organizers about football. I had just been watching football on the television. If you want to be Liverpool or Manchester United at the top of their game, then you select the players, and if the players aren't doing well enough, you have to get rid of them. That's just the truth. And not every team's like that. Not every team's like that. Not every team is playing at that level, and that's okay. But at some level, at some degree, whatever your team, that's a decision that you have to make. I'm speaking now as a leader of software teams, not just as a member of a software team. And I have had the very unpleasant duty in the past of having to fire some people, as well as the joy of being able to hire people. And I think that's part of the game. You've got to find you've got to build a team that works. If your team is genuinely dysfunctional, Why is it dysfunctional? How do you stop it being dysfunctional? If it's down to individuals, then how do you marginalize or maybe eject the individuals? How do you amplify the stuff that works? How do you get people working? You do that with pair programming, with better test-driven development, with better feedback, better opportunities to learn. On the whole, my experience has been is if you get out of the way and liberate people to do a good job, the vast majority of people would like to do that and would like to do a good job. And that's the thing. So I think you can't always be nice in all circumstances to be able to do this work, but equally you don't want to be evil and directive and manipulative to do these things. My personal approach to leading software teams, which is something that I did in the latter parts of my career, was to be open, honest, and direct, but I didn't sugarcoat things either. If somebody was doing badly, I'd say, this isn't working, you're not working. How can I help you to do better because it's not working? I would do that kind of thing. But I think those sorts of things are important ultimately. I think a lot of us tend to, I've done it in the past, tend to shy away from doing that, having those difficult conversations. And ultimately we do that. One of the things that I keep cycling back to pair programming, one of the things that I love about pair programming is it gives us a small, simple, fine-grained opportunity to just give a little bit of feedback to our teammates if they're not doing the things that we think they should be. There's a way of just incrementally just edging up the discipline in a team through peer pressure that's applied through pair programming. My preferred approach to pair programming is that you do pair programming and you do pair rotation on a regular, frequent scale. I used to, mostly in teams that I organized or worked involved in, I'd be doing pair rotation every day. So we'd swap every day. I once worked on a team at ThoughtWorks where we tried pair rotating every hour, and it worked surprisingly well, but it wore us out so fast that we all said after the first sprint, no, we're not doing this anymore. but it surprisingly it worked. But I think pair rotation matters, and part of the reason is to get everybody to work with everybody else, so everybody learns everybody else's foibles, they learn what they're good at, what they're bad at, and they just do that little thing of covering each other's mistakes. There's lots of things that I'm really bad at, and so I work best when I'm working as part of a team and other people can cover my mistakes and I can cover theirs because we're bad at different things. I don't know whether that answered your question or not really, but it's the kind of stuff that goes through my head and the kind of things that I do on the teams that I work on to try and do. The next question is, next to production and design engineering, do you think there is such a thing as method engineering? In that case, how necessary, impactful do you see the competency for agile teams? I'm not quite sure what method engineering means, unless you're thinking in terms of kind of process engineering. That might be a different way of saying something similar. So as I've said, I don't think that production engineering has any part in software development. I think it is irrelevant to software development, and that's I've said in the past, I think that's kind of the $1 trillion mistake that our industry's made over decades. And it's understandable why that mistake was made, but I think it is the mistake. And so I think it's about design engineering. And I think that, as far as I can see, that's pretty much it. In order to be able to do that, we've also got to do things like we've got to organize ourselves. We've got to figure out how we scale up. We know small teams better. So how do you give autonomous small teams, how do you organize autonomous small teams in a way so that they can build big complex software? We know the answers to some of those, and none of the answers are easy, but we know what some of the answers are. So not process engineering, no, definitely no processes. So I've not come across method engineering, so I don't know what it means. I'm sorry, I can't answer the question. Any more questions? Or if you want to define method engineering, tell me what it means.
Yeah, so method engineering is what it says in the name. is something that we learned when we were doing dynamic systems, still graduating, still students, where you apply engineering methods to define methods. It's basically the meta application of engineering methods to deriving new methods. That means you can apply it to process engineering, to chemical process engineering. So when you have to discover new ways to manufacture something, because the conditions under which you source the materials and the conditions under which you have to manufacture those new materials are completely different from whatever you've experienced in
my guess is that if I understood it more than I probably do, my guess is that I would think that it's not relevant to our discipline, because I think that the meta level for us is science. I think that applying, the fundamental principles of science to what we do gives us what we need in order to be able to apply in software. Software is this weird stuff, and it's I think it's more complicated than most people think it is, software in general, and it's complicated in interesting, slippery ways that are difficult to deal with. But it is complicated stuff. Coding's not, but software is, which seems weird, but I think that's true. And so I think that applying a bit more discipline, discipline sounds like the wrong word, because every time I say discipline, in my head, I go off on kind of imagining some bureaucracy and stuff like that. And that's absolutely not what I mean. But applying some simple rules rigorously, I think, is the answer. And those rules are largely the rules of science. So I don't feel the need for, rigor is a better word. Thank you for putting that in the chat. So I think approaching this with some rigor is the right way to think about it. And that rigor is about scientific rationalism. It's about thinking about this as a practical problem and applying scientific rationalism to solving it. That's what I think engineering means.
On that note, I think we're going to call it for this meetup. We're over our time. Thanks everyone for joining us. And thank you very much, Dave. It was wonderful having you here.
Well, it was fun. Thank you. I hope you enjoyed it.
Anything else you want to promote before you go, Dave?
Sorry, say again.
I said anything else you want to promote before everybody drops?
One more thing. If you weren't here at the beginning, I've just reposted. Thank you for showing. That's my book.
Thank you, Anthony.
Today we've just released a training course on test-driven development. It's called TDD and BDD, Design Through Testing. I'm quite proud of the course, been working hard on it. So if you know anybody that might be interested in that, there's a link in here and you can get a 10% discount on the course for today, because today's the launch and I was talking to you. I thought it'd be fun.
Excellent. Thank you, Dave.
Thank you. Thank you, everybody. Good night.
Thank you.